So as you could have seen, sports is big. Any U.S. American universities, sports is big integral part of college life. Now, or it's called American. It's called football in U.S. It's American football. Purdue is not doing very well this year, so they fired the coach this year. But Purdue is one good basketball team. So we were ranked number 1 in the country last year. For some part of time, we were in the national final championship game. We lost in the final. So, but sports very integral. But again, academics always. So you would have seen Neil Armstrong's words and Neil Armstrong statue, and there is another statue that came in between. He was John Purdue. So this also, again, a government, what we call here as government institute. There, the U.S. government doesn't give all the money for universities, but a little bit. So John Purdue gave land when this university started in 1869. That's why the name is Purdue. All other universities you will see as like with state, like University of California or like Illinois, etc. But except Purdue, since he gave land, it's his name. That's his condition. Okay, and almost all universities will have color, their own color. Like our Purdue's color is black and old gold. Okay, and we do have the last frame in that video is a mascot for Purdue. It's called Purdue Pete, and Purdue is called Boilermakers. Making boilers, but the name came for other reasons. But every universities will have a name. They will have their own mascot. They will have own symbol, color, etc. Okay. It's kind of warning. That's what one of the sentence says in alumni. Alumni network is very strong. Usually they have a strong alumni network. Alumni contributes a lot financially, and all they sponsor a lot for campus benefits. So okay. Just one video, but there are tons of videos of Purdue you can Google. So anyway, you would have seen aeronautical is big thing. One of the top program in ABE, Ag and Biological Engineering, was ranked number 1 for close to 11-12 years, but we lost the ranking for undergraduate program, lost the ranking this year. But still for graduate programs, we are ranked number 1. Similarly, almost all engineering programs are ranked in top 10, almost all, except maybe 1 or 2, biomedical, environmental, and chemical engineering are not ranked in top 10, but all other engineering programs are top 10 within, even top 5 programs, along with Stanford, MIT, and, Georgia Tech, maybe Berkeley and Caltech. So if you are interested, apply. Okay, will be a good program. You will learn lots of things. Okay, so again, as I studied from there, I can see the difference. I studied from here, India and US, right? So the culture will be a little different. So how you learn will be a little different. So there will be lots of opportunities to grow personally and professionally. There will be tons of opportunities. Okay, so let's move on. Particle size. Any questions? So what was the distribution of food that you ate today? So what did you eat? What did most of you eat? Nothing? What did you eat? Rice? Noodles? Okay. So how do you characterize particle size of noodles? Cylindrical shape, exactly, yeah. So but quantifying shape, size is difficult, right? It's long, right? So what else? You all ate noodles? No. What else did you eat? What's that? Rice. Particle size of sambar? Yeah, Yeah, it will be, very big distribution, right? Vegetables will be larger in size, right? Dal will be medium, and then you might have some suspended particles, right? Broken particles that are suspended in sambar, right? Okay, so we'll go through some of the, measurement techniques. So first one, we'll talk about microscopy methods, okay? So as we talked about, many of you would have used or seen using microscopy for measuring particle size, right? So I'll quickly go through them again. In general, if you can use any particle measurement or characterization method, but you can use any method, but still you want to use microscopy to view the particles, at least some of them, so that you will know. For example, it's a wheat flour, okay, it's about 90 micron size, but when you look, like through our eyes, it looks very spherical and uniform, right? But when you put under a microscope, you can see how irregular the size and shape is, right? So when you put under these particles, any particles under microscope, you will actually see their shape and size and difference in surface texture, etc. Okay, that will give you more understanding about the particles that you are dealing with. Okay, it can be anything. Okay, so common microscopy techniques, optical one, any regular microscopes, right? So usually their field of view is very limited, so we use them for larger particles, right? So we cannot zoom a lot, right? Some confocal, if you're using confocal microscopy, maybe you can get some three-dimensional images, but mostly we use for larger particles. Okay, so larger particles, either it can be static or moving, means you take a slide, glass slide, spray some particles on the top of glass slide, and then we put them under the microscope, and then there are tons of softwares that you can use to measure the size and shape, right? You all would have used ImageJ, right? Some of you at least. Particles like image processing software. ImageJ is very free to download software that you can use for characterizing. Okay. But if the particle sizes are small, you can use scanning electron microscope or transmission electron microscope. So transmission electron, still for very nano particle, very close to nano size ranges. Okay. Scanning electron microscope is common for, again, smaller particles which we cannot see using optical microscopes, okay, or smaller particles. Okay. But the challenge of using SEM and TEM, right? So you will have to do lots of sample preparation. Okay. It's not direct and easy like an optical microscope, so you'll have to use some gold-plated particles, spray them, and then equipments are also very expensive to use, etc. Right? But they still, can give lots of good understanding on the particles. And again, they have, higher field of view, right? So you can measure up to nano size ranges, right? Okay. So microscopy, again, in general for normal optical microscopy, you can see for larger particles, sea sand, or large any type of granules, even wheat flour, etc. But if you go down to smaller particles like pigments, paints, pigments, smoke particles, viruses, etc., then those are like submicron, right? Then you'll have to use SEM or transmission electron microscope. Okay. Any questions? Any of you use microscopes for measuring particle size? No? Okay. So again, you can get the shape and size from the same measurements. Okay. So one of the major disadvantage of using optical microscope, it's from two-dimensional projection, right? So how are we characterizing is from the two dimension, from the field of view, right? How we see the particle, right? So if the field of the projection changes, the particle size will also change, right? So for example, if I am seeing this as from the top like this, the size is different. But if I am seeing like this from the top, the size is different, right? So the particle orientation or the projection will highly influence how we characterize the particles. Okay. So that's one big, disadvantage of using microscopes. Again, lots of sample preparation is needed. Size distribution, as we just talked about, before lunch, it gives by number. So if you're using lots of a number of particles, then your distribution might be different than a smaller group of particles. Okay. And again, preparing particles will also be a little challenging when we prepare for measurements. Okay. So what are some of the microscopy, you would have, at least ag engineering students would have learned about some size measures that we calculate from microscopy technique, right? Anyone? Any? What are some of the size measures that we calculate for particles? Obviously one is size, right? What other, characteristics that we calculate? Shape, okay. What is it? Diameter, okay. So what are the shape parameters that we calculate? Okay, exactly, that's what I was looking for. Sphericity, circularity, etc., right? So from the projections, right? So common, size measures that we use again or calculate from the microscopy technique. Okay, one is again that circumscribes the particle. Okay, you draw a circle around the particle, and based on that diameter, you calculate the size. Okay, the other is minimum chord diameter. Again, that's within the particle, internal projection. Okay, the smallest circle that fits within the particle, and then you calculate the size based on that circle. Okay. Other things, you would have learned about Ferret's diameter, Martin's diameter, etc. Right? Ferret's diameter, again, the projection, external projection of the particle. Again, with the change in orientation, the size will also change, right? So it's not unique. So you can have more than 10 values, for one same particle. Same, for Ferret's diameter and Martin's diameter. Okay. Ferret's diameter, again, based on the projection, and Martin's diameter is from the projected area. So the line or chord that dissects the particle into two equal areas. Okay, so that's the Martin's diameter. Okay, again same thing, like Ferret's diameter, Martin's diameter is also not unique. Based on the projection, this value can also change. Okay, so how do we use these values? Okay, okay, one more thing. So that unrolled diameter, again unrolled diameter to get accurate size based on the projections and shape variations. Okay, so you get the diameter or the radius of the particle across 360 degrees, and then you calculate the overall radius from when you unroll a particle. Okay, so it gives an accurate mapping of the particle based on the irregularities or the surface irregularities. Okay, one of the challenge will be, if you have overlay particles, two projections, then you might get two values, right? So then you get wrong values. So you may not be able to use that if you have overlay projections. Okay. Okay, so we use these projections to get, different values like equivalent circle perimeter diameter, equivalent circle area diameter, volume diameter, surface area diameter, etc. Right? You all know these equations, right? So the area for a circle, you calculate from the diameter, same area projection from the diameter, right? Volume from the spherical particle, right? Volume and surface area, and then surface area to volume diameter, right? You all know these equations, right? You remember at least, or if you don't, make sure you remember, okay? Because we will be doing some calculations now, okay? So okay, calculate these. So for the cylinder particle, it's not a noodle, okay? It's a small particle, okay? Small cylinder, 10 mm by 50 mm size. The equivalent circle area diameter, okay? Equivalent sphere volume diameter, equivalent sphere surface area diameter, and the specific surface diameter. You all remember the equation, or do you want me to go back to that slide? area diameter. Still I show that questions. I know we have 4 BS agriculture students. You may not study all these things, size and shape. Do you? No. What's that? Any question?
No.
If you're bored, you can also do the calculations. What? What? Yeah, yeah. See, you know the formula, you can calculate. Okay, so anyone got an answer for the first one? Okay, I'm not sure the value though, but what I got was 25.24. Okay, and make sure, assuming the cylinder lies on its cylindrical side, so this is the projection that you are getting, 10 by 50. Okay. So for equivalent circle area diameter, okay, so you can get the projected area, right? So you know the projected area of the cylinder. So what you are calculating is dA, right? So you calculate dA, okay? So that will be the equivalent circle area diameter, okay? Okay. So anyone got the value for sphere volume diameter? Next one. Did you? How much? 19, exactly 19.57. So, anyone for the third sphere surface area diameter? Do you get? 23.45. The last one? So again, the formula, yeah, my sphere surface area to volume diameter again, left. What's that? 13.64. Again, these are, this is how you calculate if you're using, automated image analysis softwares like ImageJ and etc. Okay, so based on from the projection, you calculate those diameters. Okay, so again, particle shape factors, as we talked about, the orientation changes the particle size, and also, the shape will also affect the particle size, right? This is microscopy technique, right? At least for microscopy technique, right? So there are, shape factors. I will not, go much detail into it. Shape factors that you can use to convert or calculate these, particle sizes from the volume, from the surface area, or from surface to volume ratio too. Right? This gives a little bit, close approximation to the change in orientation or change in shape when you calculate the particle size. But when you use, shape factors, usually you increase the error in characterizing. Okay, so the error also increases, along with the use of different shape factors. Okay? But again, we'll talk about shape factors a little bit more when we talk, when we go into particle size distribution. Okay. I'll skip this one again, this shape factor. So microscopy, when you use any microscopy analysis or software, this is again from Malvern, G3ID that uses optical or slides to get the particle characteristics. You get almost all the size and shape values like, convexity, circularity, perimeter, length, width, circle equivalent. So CE here means circle equivalent diameter. So it's two-dimensional projection, right? So it's taking the particle as a circle, okay? Not volume, not a sphere, it's a circle. Okay. So from that circle, any shape material, again you get the CE diameter. Okay. So you can see from this, if the aspect ratio is high, then the values that you get is very wrong here, right? Because this is not even close to a circle, it's high aspect ratio particles. Okay. So if the particles are very close to circle or spherical, then microscopy will give a good result, but not for high aspect ratio particles, not for noodles. Okay. We still can, calculate, particle sizes, but it may not be very accurate or, very close to the size that we see. Okay. Any questions? So there are, again, for microscopy too, there are of standards. If you Google, British standards, ASTM, ISO, etc., that you can use for that gives, these standards gives different, size measures based on two-dimensional projection. Okay. Okay. Move on to light diffraction. Okay. So light diffraction is simple, right? Simple technique. You would have, many of you would have used Malvern or any kind of, laser diffraction measurement, right? How many of you used a laser particle size analyzer? No one? You have? You should have one here, right? In food engineering?
It's there, but it's not working properly.
Oh, okay. Okay. Is it a Malvern? Yeah, okay. Okay. So again, this is a very, simple and easy, simple to measure and easy technique. Okay. If you would have used, you will know, it might, you get the particle size in maybe in a minute or two maximum. Okay. So you load the sample and it gets, you get the report. Okay. Very easy, very simple measurement. So it's depending on the technique or, the measurement is based on light diffraction, how much light is diffracted from the surface of the, particle. Okay. So again, we can use for a wide range of particle. So compared to microscopy, this method uses or compare the particle to a sphere, a spherical, identical spherical uniform shaped material. Okay. So in microscopy we are using circle, but here we are using a sphere. Okay. So it gives a volume distribution. It compares the volume of the particle to the volume of a spherical, uniform material. Okay. Again, couple of methods. Either it can be in suspension in liquid or in air too. Both are common, but most used is the liquid, dispersion systems. You suspend the particles in the liquid, they will be, it will be circulated in the liquid, and then light or laser pass through it, and then from the diffraction you get the, particle size. Okay. So how it works again? Usually there will be a chamber through which, the particles are suspended. Okay. So laser or light passes through the, those particles, and then based on the diffraction, smaller particles will have a larger diffraction and larger particles will have a smaller diffraction. So the instrument again collects all the diffracted information, and from the collected information you get the size, shape, volume, etc. Not shape per se, but size, volume, surface area, etc. Okay. So again, it all keeps on summing the data. So one of the major challenges, it's based on diffraction, right? So it's limited by the concentration. So amount of powder that you add or particles that you add in the suspension should be limited so that you can quantify all the diffraction. It's not overloaded within the load cell, within the cell. Okay. So do you guys learn about light theory, etc.? Theory of light, little bit? Ag engineers? No? So you might have learned, heard about these scattering theories, right? So Fraunhofer scattering, me scattering theory, Rayleigh-Gantt scattering, etc., right? So different instruments, why I asked Malvern means, different instrument uses different scattering theories. How they collect those, diffracted, information from those particles. Okay, so mostly, you might see in the instruments, Fraunhofer and me scattering theory, mostly for particle sizes larger than 2 microns or around close to a micron and submicron particles. Okay, but if it's small, particle diameter much lesser than light wavelength, etc., then you use different scattering techniques or scattering theory. Okay, and there are tons of theoretical literature on these scattering theories, and then useful how they are used for particle size measurements. Okay, so again, most of it's Fraunhofer and me scattering thing. So as I said, rapid analysis, very quick method of measurement. So within a minute or two, you get the particle size, surface area, etc. But it also comes with some challenges, right? So one is the limit of suspended amount of particle that you can have in suspension. Okay. The second is we should know the optical properties of the material. Okay. So that's a baseline that you wanted to, know. So the instrument, when you measure, it will ask for the optical property of the material. Right? But if you are buying a instrument such as Malvern, usually for all common powder particles, they will have the optical property listed there. So you don't have to go and measure it, but you just choose the appropriate optical property. One other major disadvantage, again, it assumes spherical particle, right? So if the particles are of high aspect ratio, then the error in measurement will be very high. Okay? If you are measuring for noodles, the error will be high. But if you are measuring for like tennis balls, then again, we may not measure for tennis balls, but they're very close to sphere, right? Then the error will be very small. Okay? So if it's close to spherical, less error, but if high aspect ratio, then the error percentage will also go up. Okay? Again, optical properties, again, how it corresponds to the, the measurement is very important. Again, I think it's simple measurement. If you have a refractometer, you can measure the optical property, but if not, most of the instruments will have the optical property listed in there itself. Okay. So this is an example report from Malvern master size. So you can see, you'll get the specific surface area other than the size, surface weighted mean diameter, volume weighted mean diameter, etc. Okay. So D3243, etc. I think we'll talk about those numbers, in the next particle size distribution when we talk about, distribution. Okay. So other than size, we get some surface area related measurements too. Okay. So and again, it gives a very nice plot of volume distribution. Okay, particle size and how much percent volume of that particles are within that mix of powder that you are measuring for. Okay. Any questions? How many of you are feeling sleepy already? Was the lunch good? Okay. Okay or good? Okay, good. Okay, so the next one, focus beam reflectance measurement. Again, very similar, using laser. Okay. If you worked in a dairy industry, not milk, but dairy industry mostly. So this is very commonly used in by the dairy industry. So if you are processing milk into different products, like preparing, making yogurt, okay, or other products. So you'll want to see the protein fragments in those, right? So proteins are usually, high aspect ratio particles, right? So for continuous formation of or continuous measurement of protein suspension in those milk products, they commonly use this focus beam reflectance. So as I said, mainly for high aspect ratio particles, since it measures the chord length, okay? So it measures the chord length of the particle, okay? So by again passing, passing laser beam through those particles, and again from the duration of reflection from those particles, you get the chord length of the particle that's suspended within that, any medium. So why I said, dairy is very common user of this FBRM, technology for making different products, okay? Mostly for, process situations, so you don't use it for, particle size measurement per se, but to monitor the process changes, okay? So I said, how much protein particles are forming within, or how much it's suspended within that medium, that you are manufacturing, etc. So mostly for online monitoring, and then again measuring the chord length. As I said, for mostly for high aspect ratio materials, right? Any questions?
How much sample we require for
This is again for online. So if your process depends on process, you don't need a lot. So if it's a small batch process, you can still use some.
this? It's not in a milliliter.
Yeah, it will be mostly for process, like liters. Yeah. Any questions?
So is it suitable for only liquid food or solid food?
Mostly suspended solids. Yeah. So if it's pure solid, they don't use it. It's mostly for suspended. Like I said, dairy is very common example. Or, crystallization. So in pharmaceutical industry, you might know, right? So those medicines are formed by crystallization technique, right? Crystallization. So how the crystals are forming during that process, they use this, FBRM is common, okay? Because crystals, again, high aspect ratio, right? Usually they are not spherical. So the other common, again, light extinction common method is how much light passes through the particles, okay? So based on the light that passes through the suspended particles, you can get their size, okay? Again, there are, different theory associated with it. Again, how much, in general, it's how much light passes through the cloud, okay? So if there are, smaller particle, again, the diffraction will be larger particle, less diffraction. Again, if it's suspended thick as a cloud, then the, extinction will be high. That means the light doesn't pass through it. But again, it's not, not used for, most not used for large particles, but, very common for smaller particles, okay? Again, based on how much light passes through the, cloud. Okay? So said samples, must be very similar to, the laser diffraction or light diffraction theory. It should be in dilute suspension. If not, you will be doing like overcrowded particles with, but you will not be able to map all the particles suspended within that, medium, right, within that cell. Okay, the dynamic light scattering, you might have maybe seen this, this common again, mostly for submicron, very small particles which have lots of Brownian motions. Okay, larger particle you may not see Brownian motion, right? So they just suspend and then they settle down, right? But if the particles are very small, they will be moving around a lot, right? Like dust particles in air that's suspended, they will have lots of Brownian motion, right? So, for those type of particles, this is common technique, dynamic light scattering. Again, very similar principle, pass lights, pass through the cloud, and based on the, reflection, then you calculate the size of those particles, okay? Mostly for very small, close to nano size ranges, okay? So 3 nanometers up to about 6 microns, which we see, commonly in this range where you see a lot of, Brownian motion of those particles. Okay. And polarization intensity differential scattering. Many of the light, measurement techniques is limited by the size of the particle, right? So the Spitz technique uses different wavelengths, so you can capture different sizes of particles within the same instrument. Okay, so if you have a mix of very close to nanomicron, nano size particles and some, mix of micron size particles, then the other instruments may not be able to accurately quantify, but Spitz can, quantify this highly, distributed particle size mix, from small to large. Since you, as you can see, they will use different, scattering angles, here from larger scattering angle to smaller scattering angle, so that you can, capture any different, sizes within that mix. Okay. It's not very common, but, this technique is also available out there. Okay. And there are many different standards, ASTM, British, ISO, etc., that defines, these standards of particle size measurement using light, reflection, refraction, absorption, etc. Okay. Okay, any questions? Any questions? No questions? So we'll talk about sieving, okay? Sieving is a common technique, right? So how do we use sieving? So you take a stack of sieves, right? So how do you decide which sieve to use? What is that? Someone said something.
According to mesh size.
Mesh size, okay. So you follow some standards, right? So depending on the sieve opening, right? Okay, so again, a sieve usually, a pan with openings, and again, you might see different, sieve openings based on the size or distribution of particles that you wanted to measure. This is the least expensive method, right? When compared to microscopy or laser diffraction, etc., you just need a set of sieves and some shaking mechanism, right? You shake for some time, and then, you get the particle size based on the amount of samples collected in each sieve, right? So very easy method, and very simple method too. So there are, when you take sieves, there are different types of sieves. Some of you, if you have used sieving techniques, you might have noticed, right? So if you change the standard of the sieve sizes, then the openings may not be the same. Okay? So it depends on how the sieve meshes are formed. Okay? So if it's electroformed, it's more uniform and close than a woven wire sieve. Okay? If it's woven, then the size may not be accurate. It's more than rectangle than a square. Instead of an electroformed sieve. So electroformed is mostly precise than the woven wire and the perforated ones, but in general, it's little expensive. Most commonly used for smaller particle size sieves. Use those electroformed sieves, but very commonly for large particles, we either use perforated or woven wire. Okay. So again, there'll be high tolerances. Again, 10% or 5 to 10% variation is also there due to this difference in opening. Okay. One is opening, difference in opening. The other is how the particle fall through the openings. Okay. If the orientation changes, then the size might also change. Okay. And mostly we measure the chord diameter. Okay. So depending on the orientation of the particle, so what we are measuring when it passes through the sieve is the chord length, okay, of that particle. Okay. So again, minimum, the maximum, chord length that fits within that square opening will allow the particle to fall through. Okay. Again, we calculate the arithmetic mean diameter again based on the amount of sample collected in each sieve, right? Any of you use sieving calculations, like particle size from sieving? No? Any of you used? You have, right? So which standard do you use? Anyone remember? Taylor series. Okay. How do you calculate the particle size or the arithmetic mean diameter? Anyone have used? At least ag engineers. You may have used ASAB standard, right? You might remember? No? So from your undergrad labs, when you go back and check, you might have used ASAB standard, okay? But in general, again, that's the arithmetic mean diameter that we use, okay? But as said, there are two different types of, actually three different types of, sieves, series like ISO, ASTM, and Tyler. Tyler and ASTM are common, I believe. ISO maybe, but most sieves that we use, either it should be Tyler or ASTM standard sieves. Okay. Again, successive sieve apertures usually follow a 2 power 0.25 size openings, are mostly for these standards, but except for French standard it's 10 by 10 the power 1 by 10. Okay. So again, approximate progression is about 2 power 1 by 4. Okay. Okay, so can anyone solve that? It's easy. How do you prove that the successive opening sizes increases or goes in a progression of 2 power 1 by 4? You can do that theoretically. Anyone taking a shot? Anyone trying? You're clear on the question, right? No? What's that? Okay, so can you prove the progression of aperture sizes follow this rule, 2 power 1 by 4? Sure if I have that in the slide, but again, I've shown all those sizes here, and you can get from all the standards to the opening sizes depending on different sizes here. Okay, but I have the answer there too. I don't want to show the answer. But anyone want to try? You don't have to use any values theoretically. So how does it, how does the particle falls through? Maybe it's much, maybe I'll show the answer, okay. So just showing how it changes by 2 power 1 by 2, okay. So if you're assuming the particle sizes, and if you know the, if one major assumption that we make is, the shape doesn't change, okay. But in general, that's not, true. In general, the shapes may not be common or same for the particles that are passing through different opening sizes. Okay. So again, from the surface characteristic, surface from the shape factor, and you don't have to use the shape factor, but assuming shape factor is constant, you can know that particles or the sieve sizes use the formula of 2 power 1. Okay. What is any question? Okay, so typically, so if we talked about using arithmetic, mean diameter, right? In general, again, we are using the weight of material to get the size, right? So many people, many times we don't use that arithmetic mean diameter, but the normal common, convention is using a positive negative sign, right? So a plus 40 minus negative means the sieves, for example, plus number 4 plus, minus number 4 plus number 40 means, more than 90% of the powder will pass through number 4, but again then retained at number 40 sieve. Okay, that's a common convention. So that gives a distribution. Okay, it passes through this opening, but it retains at this sieve. Okay, so the size of the particle will be within this range. Okay, so that's a common again convention. Again, or percent of material that's retained on each sieves. You get a distribution. Okay, so you get the amount of sample retained on each sieve and then calculate the distribution of the particles based on size. Okay. So I'll not go through a lot. So most of you would have used sieving technique, right? So common vibration method, but if the particle sizes are small, then you could use air jet sieving or supply, use some additional air, okay, so that it flows through the openings very easily. If you fluidize them, it flows easily. If it's little cohesive or agglomerate, if the powders have little agglomerating tendency, you might want to add some flow aids or some dispersants like stearic acid, fumed silica, etc., that makes the particle to flow easily through the sieve openings. Okay, if not, kind of clog. Okay. Wet sieving is also common, again if they doesn't dissolve in liquid or water, but you can use other alcohol medium or alcohol solution too. But that gives little better accuracy for cohesive powders. When you're using in a liquid medium, you avoid formation of agglomerates, small agglomerates, so it gives the measure of individual particles when it flows through the sieve, okay, rather than large agglomerates. Okay. But if you have larger size distribution and if you wanted to use sieving method, so one of the suggestion that we provide is first separate them into two small two large, one large particle group and one small particle group, and then measure them separately, okay, instead of having to use a large array of sieves, okay, large number of sieves. Again, how much time we use for how much time we have to sieve, again there are different equations that we can use to calculate the amount of time that's needed, but most of the powders, if you check any standards, they would have provided the minimum amount of time that you have to sieve any powders, right? It's usually about close to 10 to 15 minutes, anywhere from 10 to 15 minutes of sieving. But if you do not know the time, ASTM standard suggests you sieve them or vibrate them till there is no more than 0.5% difference in the sieve samples or the sample weight. Okay. Again, so usually by distribution by mass, and again in general you have to monitor for the weight change during the sieving process. Okay. And this is a simple method, almost you all would have used, right? So most commonly we get the distribution, either cumulative distribution or the frequency distribution, to get more in-depth analysis of the particles, right? So you can get D10, D50, D90 or 90 particle size, you can get the span, you can get other meaningful information from this distribution too, right? Most of the distributions or any distributions, but based on the amount of samples you can get the distribution. So I'll skip this. And for ag engineering, we commonly use this ASAB standard for using sieving for different particle sizes, but there are tons of other standards. ASTM, if you're using flour or food related material, ASCC, American Association of Cereal Chemists, also have a standard for sieving of food powders. Okay. We'll quickly go through this. I do have another online meeting at 4 p.m. So hopefully, and then I think Dr. Gotke will be teaching the next class. Right. So we'll quickly go through the fluid-based measurements. So you would have known about Stokes diameter and aerodynamic diameter, right? Stokes diameter again uses the principle of Stokes law. Okay. So if your particle is suspended in fluid medium, okay, in general, the weight, the force from the weight goes downwards, and then the drag force and the buoyancy force tries to balance that if the particle needs to be suspended in that fluid medium, right? So all those equations, drag force, weight, inertia, and also buoyancy force. So you equate them and you get the particle size, provided you know all the viscosity, you know all the other important stuff, viscosity, density of particle and the fluid, etc., and then you can calculate the Stokes diameter. Okay. Again, there are instruments that we'll talk about that in a minute. So one other major assumption here is we are assuming this as a spherical particle, right? That's one of the basic assumptions that we use in Stokes law, right? The particles are spherical, right? So again, for high aspect ratio, the values might be little different or little error, when you use Stokes principle. Right? So sedimentometers, I'm not sure if any of you used, it's very common that uses Stokes principle. Like you suspend the particle and then measure the amount of time or monitor the amount of time that it takes to travel from some distance within that sedimentometer or from top to bottom. Okay. So from based on the time and the distance, you can get the terminal velocity, and if you know the terminal velocity, you can use that Stokes law to get the diameter. Okay. So advanced sedimentometers uses X-ray again to get more accurate determination of their height and time when it passes through the fluid medium. Okay. So major advantage, we can go up to about 50 nanometer size particles using this technique to get the particle size. Okay. So some of the important things that you have to keep in mind. So the difference in particle density between the particle and the fluid should be high enough so that you see the difference when the particles are settling or moving through the fluid medium. Okay. So if they are very close, you might not see the difference at all. And again, if the particles are different in density, then you might get error in results. So almost all the particles that you are using in the lot should have very similar identical density values. Okay. If not, that will be little errorful. Again, temperature will be the major important, and again, dispersing liquid, deagglomeration, etc. Careful consideration that you have to keep in mind when using this liquid method or Stokes principle. Okay. Same like other methods, very simple and easy measurement. Aerodynamic diameter, very similar principle. Only thing we are not using any liquid but using air to suspend. Okay. So similar depending on the force equilibrium. Okay, you can again same using the Stokes principle. If you know the aerodynamic drag, if you know the weight of the particle, the buoyancy force, you use them and calculate the diameter. Right. So again, same settling velocity. Again same spherical particle assumption is valid here too. Okay. Okay. Can anyone give an example of why do we apply this aerodynamic diameter? It might be a little long reach, but any example?
Particular effect of force from all sides, like it has some tension.
Which one can?
Tension, it has some
Tension. Tension, yeah, no, may not be.
How much force required to lift the particle?
You can.
Classification.
What's that?
Air classification.
Air classification very close, yeah. But you can, what's that?
Cyclone separator.
Cyclone separators, yeah. Cyclone separators are very closer. Okay, how much air will interact with the particles, right? So cyclone separators, except not pneumatic handling, but cyclone separators, little bit of air jet sieving, etc. But that's air classifier will overlap in both sieving and also in this aerodynamic principle. Okay, but cyclone separators might be, you know, very common. Okay, but you know, it's, we don't use this technique much in food. Okay, very commonly used by the pharma industry. Okay, any of you use inhalers? Inhalers? Inhaler, right? You know, sometimes, any kind of inhaler, it could be medicine or aerosols, etc. So that's, very common application of aerodynamic diameter. Okay, when you are using inhaler, how much amount those, if you're using medical inhalators, inhalation systems, how much time it takes for the particle to settle in your lungs, how much time it takes to reach, to the lungs. That's, very common example. So they use a specific, instrument for this. It's called the inertial factor, for finding the, aerodynamic diameter. As I said, it's for very small, close to nano-sized particle range. Okay. Again, when the particles pass through this, it suspends and settles into different columns, within that instrument, and then based on how long it passes through that will decide its, diameter. Again, very commonly used in pharma and, mostly inhaler, suspended particle manufacturers. Electrosensing, another common, number-based approach, again, based on counting the number of particles, but it can also give a volume-based distribution. So this is also a very common instrument. You might have seen one, or you may have one here. It's called the Coulter method. So simple measurement, so the particles are suspended in fluid medium, and when it passes through the electrodes, with the change in voltage, its particle size is, calculated. Okay, so the change in voltage corresponds directly to the size of the particle. Okay, so again, that's again simple measurement used for, again, assumption of spherical particle is valid here, 0.6 to 800 size. Okay, and it's also, again, it's not very common as laser diffraction, but it's also this counter is also a common instrument that you might see in many places. Okay. And again, some standards, ASTM, ISO. So coming to almost close to the particle size lecture. So the common, size measure, particle size, is the almost the most important property that we measure for any particle materials. Okay. So it influences all our design, handling, whatever calculations we are going to make will be, influenced by this, particle size. Okay. We can use any different techniques, but the suggestion would be at least put some of them under microscope and see how they look like, at closer, it gives more information about, the particles itself. Most common, again, as we talked about, laser diffraction and sieving. Mostly if you go for industry, most common is, the laser diffraction. It's very quick and easy. Almost all industry will use this, laser diffraction technique. Okay. Again, comparing two different techniques is not suggested and advised. As we talked about, we use different physical principles, so you don't have this, you're not comparing the same sizes, from different measurements.
Hello, check.
So check this text, it's not a textbook, book by Allen on particle size measurement. You have lots of theory behind all these, particle size measurements in that textbook. Okay. It's not, it's not a textbook, it's a book. Any questions?
So
51. This one?
What does it mean by 0.5% mass difference? You told that the time should be up to 0.5% mass difference. I didn't get that.
So this one, right? This line, right? So many of the standards will have specific time, right? For example, if you are measuring for wheat flour, you will have to sieve for, I think, 12 minutes. Okay. But if you do not know the time, how much time will you sieve the sample or run the vibration system? So the common, suggested by the standard is you sieve until there is less than 0.5% mass difference between two sieves.
Between two six.
Sieves, yeah. So, for example, if you have one sieve, 20 micron sieve on the top, 10 micron sieve on the bottom, okay. So if after you sieve for some time and check the weight of both 20 micron and 10 micron, if there is some change in weight, you still continue sieving.
Mainly the overflow that is staying over the screen.
Yeah, over there,
Okay.
yeah.
Over these two successive
Yeah, over the
states.
successive sieves, yeah. So,
That difference should be 0.5%
yeah, less
between
than
these two.
0.5%, yeah.
Okay. Okay, sir. Thank you.
Any other questions? Yeah, go ahead.
Sir, my question is general, like if we want to do a milling and we need to optimize it, so how can we approach this, like by particle size distribution?
Okay.
Like we need a particular size range, let's say 40 micron. So how should we optimize that milling process?
So, you'll have to do lots of things. So, for example, if you wanted to optimize the milling, so in the current industry setup, how do? They do, calculate the particle size in between during the process. Okay. So, during milling, they calculate, or they take subsamples and then calculate the sizes. Okay. In general, there, at least in wheat milling, since you said wheat milling, technology is very advanced. They have perfect sieves, sieving mechanisms, air purifiers, etc. That gives very close approximation of the or close particle size ranges. Right. So, only thing is, you take sample and measure the sizes, and then adjust your process till you get that size.
Okay.
Right.
Sir, if we have this lab scale equipment like ball mill and hammer
Yeah.
mill, in that we can do that.
Yeah. So, so large process or small process, you can still do that.
And which method will be suitable, sir, like laser one or the sieving one?
So, again, depend on your process. So, if you are interested in more spherical related thing, then use laser. But if you are, just wanted to see the process change, the process difference, then sieving will be easy and convenient. Okay. Sieving will be easy and convenient,
Yeah.
but if you wanted more accurate, then laser diffraction will be better. Yeah. But but if if you have money, you can have an online system too that quantifies the particle size continuously. So you install a laser system. Okay, inside that whatever milling
unit.
system, milling unit, and then you continuously characterize. I'm not sure. Have you heard of an industry called Bueller?
Yes.
Bueller, yeah, Bueller manufactures lots of process machines, right? They do have an inline or whatever online, particle size measurement system, mainly for milling and grain processing industry. When the flour comes out, it gives the automated, particle size. So,
Thank you, sir.
yeah, no problem. Any other questions? No questions? I see that you are relieved that I am stopped my lecture, right? More satisfied faces. No, I'm just joking, but well, we'll talk about particle size distribution tomorrow, right? Tomorrow, what time? It's 9. Okay. Okay, so any other questions? But come up with more questions tomorrow, okay? Think about it. You don't have to sit and think while walking. If you come up with some questions, we can discuss more. Okay.